most essential experimental aspects of past and future heavy ion physics. So we can see your slides, okay,
Okay,
and you
can you hear
could
me?
start anytime.
Can you hear me?
Yes.
Okay, very good. Okay. Yeah, thanks. First of all, I want to thank, of course, the organizers. So I was asked to give this overview talk about the essential experimental aspects of past and future experiments. This is, of course, a big topic. So I will focus actually on a few key developments of detector technologies and evolutions. I was asked, of course, to give a talk which is not going too deep into technical details, so don't be worried. And if you have questions, of course, we have time then to discuss those after my talk. Let me first start with an overview of what we think are important features of experiments. So there are a few general features we have which are important whenever you plan and build a detector. For example, which kind of acceptance do you want? What kind of coverage in azimuthal angle and pseudo rapidity you want to have? What energy coverage you want to have in, for example, in transverse momentum? Do you need particle identification capabilities, and then which ones only charged particles, so also, for example, d zeros and so on. And for this, you also need to have special vertex resolution. Momentum resolution is, of course, always important. Data taking rates are getting more and more important over the last 10, 15 years for looking into rare probes like D mesons and so on. Software and electronics, for example, chip development, that's of course also a huge topic. I'm not going to talk about those things in detail here. This would be actually a talk for itself, but you can imagine that there is an interaction between detector technology and the software and electronics you have. So usually we distinguish between two different kinds of experiments, ones which are placed at a fixed target accelerator, and ones which are at colliders. So for fixed target, you usually deal with cheaper accelerators, usually lower energies in the center of momentum frame and higher event rates. For colliders, you have the highest energies in the CM system. The event rate is increasing with energy, and an advantage is that your CM frame is actually the lab frame. And this is not really the case for fixed target collisions. That's why I wrote here complicated acceptance. This is sometimes actually a kind of an issue. I say here lower and higher because things are actually changing. We have now colliders at low energies with high rates. We have fixed target experiments at higher energies. So this is just a tendency, but usually we distinguish, of course, also the experiments, whether they are placed at one of those two different kinds of accelerators. So in this table, I summarized the historical evolution of the various facilities and experiments we have in heavy ion physics for the past 40 years. So starting with Beverluck at Lawrence Berkeley National Lab, going to Synchrophasatron at Dubna, AGS in Brookhaven, then SPS at Geneva, SIS in Germany, in Darmstadt, then relativistic heavy ion collider in Brookhaven National Lab, Large Hadron Collider at CERN, SIS 100 at GSI Darmstadt, and now also the nucleotron in Dubna. At each of those facilities, there were usually various experiments. Of course, I'm not going into the detail of all of them, but I will give you some historical context and show you how the detectors and experiments evolved over time. I highlighted here a few experiments, Chaos, Halo Star, and Alice. Those are actually the ones I personally worked on. So if I talk a little bit more about those, so then the reason is I'm a little bit biased here. You see here the different facilities have very different energies. So at Beverluck, a few GeV, at LHC, we have the highest energies of about 5 TeV in square root S. So before I come to the experiments, I give you some brief overview of the accelerator facilities. So starting with one of the oldest ones where heavy ion collisions were conducted, the Beverluck at Lawrence Berkeley National Lab. So the super high luck You have a linear pre-accelerator here on top of the hill. Then you had a downhill transfer line, so that's not a joke. And then you have the synchrotron here, and then the experimental hall. So this was about a maximum energy of about 2 GeV in fixed target mode. This was, of course, not a perfect place to build an accelerator. So this was built on the Hayward earthwork fault line. And of course, there was limited space, so it couldn't really be under reasonable conditions expanded to higher energies and so on. So I was there for about 7 years in Berkeley. I still saw this kind of this hall, and then it was removed and replaced by actually a parking lot. So we have at similar energies as a Beverluck, we have the SIS, this stands for Schwer-Ion Synchrotron 18 accelerator complex at GSI in Germany. This goes also to energies of about 2 GeV. The extension you see here, this is fair at the SIS 100. Even it looks like a collider, it's actually a synchrotron with fixed target experiments. And this goes up to about 5 GeV and will be in operation in a few years from now. So here you see actually a picture of this fair complex, how it looked like a few weeks ago. So this is under construction. Also under construction is the NICAR at JRNR. So with an older part of the complex, you see here the nucleotron, and then the newer part, which is actually a collider. And the big advantage here of this facility is that it actually covers a very interesting energy range here from 4 to 11 GeV in square root S with a very high luminosity. So I will give you also the numbers at the end of the talk. So that's a specialty of this facility in Dubna. So now we come to the big colliders, the relativistic heavy ion collider RIC at Brookhaven National Lab at Long Island, close to New York, 3.8 kilometers, 2 rings with 4 major experiments. But I will talk only about the Phoenix experiment and the STAR experiment. Here the square root S is 200 GeV maximum, but as I will show you, there's actually a large energy range those experiments can cover, and also the collider can perform. So the largest collider and accelerator we have is the Large Hadron Collider LHC at CERN in Geneva, 27 kilometers, 5 TeV square root S maximum energy for lead collisions, 4 major experiments, but I will talk only about the ALICE experiment, the dedicated heavy ion experiment. So for ATLAS and CMS, I have actually slides in the backup. So now I come to the important aspects of the various experiments. And as I pointed out before, I'm not going into the detail of all the experiments, especially for the older experiments. I will just briefly point out what the important aspects were and how they actually evolved into the newer experiments. So I start with one of the, or maybe the original heavy ion experiment, the GSI Lawrence Berkeley Lab plastic ball experiment at Beverluck. So the accelerator facility I just showed you. So this here we had about 800 telescope-like crystals and scintillators, which were surrounding the target, which was somewhere in this ball. And for various reasons, this is a kind of a unique experiment. So first of all, it surrounded really almost the full target area, so 4 pi coverage, which is quite unique, I have to say, even nowadays. And the second point was there was no magnet. So the particles were identified and detected by those telescopes here with crystals and scintillators, and you measured the total energy and the relative energy, and by plotting them against each other, you could do particle identification. So you could distinguish protons, neutrons, and even pions. So this was one of the first ones, and here you see an actual picture of it. So you see Hans-Georg Ritter and Art Postkanzer. You see the plastic ball experiment and the forward TOF wall. And one of the major findings here was their identification actually of flow. So one of the first pictures showing that there is flow in non-central heavy ion collisions. So now I group the rest of the experiments actually into three different categories. So I start with those which are based on drift chamber tracking detectors. I will explain this in a second. The second part is then about time projection chamber based experiments, and finally about silicon based experiments. So the first one is a Dls experiment. So it stands for Dielectron spectrometer. This is was also at Beverluck. You see here those chambers, so even either drift chambers or multi-wire proportion chambers, in that case drift chambers. Those are actually gas-filled detectors with some wires in it, high voltage. And you could identify particle tracks on a small scale, so on a few centimeters usually. So you had a few hit points. You had hit point here, and the hit point here, and then some bending in the magnetic field. And with that, you did tracking, reconstructed the momentum. And what is also special for this experiment, because it's a Dielectron spectrometer, you need to do particle identification. So you had Cherenkov counters here for high-speed particles and time of flight walls at the end. And this kind of setup we will see actually many times, even in one of the latest experiments. As you see, this was a two-arm spectrometer, so the acceptance was quite low. So the electron positron, they had to go in the two arms at the same time in this direction. So, and the readout rate was relatively low. So in total, they got only 30,000 electron positron pairs, but this was enough actually to get some first dielectron spectra. The next evolution in this kind of physics is then actually the high acceptance dielectron spectrometer. So you see the names are very similar, but the improvement is high acceptance. The acceptance is in polar angle much larger, so 15 to 85 degrees. So the target is somewhere in here. This is an explosion view actually. And full azimuthal coverage. This was not the case for the Dls experiment. Another big advantage is that the high data taking rate of nowadays up to 10 kilohertz for gold in the peak. The rest of the detectors are actually very similar to the DLS, a Cherenkov detector, in that case a ring imaging Cherenkov detector, and time of flight detectors to measure the speed of the particles, and with that actually the mass. And this is also used for particle identification. So some of the key results you see here, so a Dielectron spectrum from silver, just from recent years. In black, the data points, in red here, the curve is the cocktail, and you see some enhancement here in between. Actually, it turned out that this detector is more a multi-purpose detector, so it could also reconstruct off-vertex decays like lambdas, and also doing particle identification for strange particles, for example, phi mesons and kaons. So, and this is actually what is nowadays more the case, that you have multi-purpose detectors and not detectors which are specialized on one unique reconstruction of a single type of particles. So only briefly, I will mention the Chao spectrometer. So this stands for kaonen spectrometer. You see here the operation time in the 90s mainly. This is what we call a keyhole experiment, because it had actually a tiny acceptance. So the target was here, and then the particles were going into a very tiny acceptance into this dipole where the particles were bent. And then you also have those, in that case, multi-wire proportion chambers. So you also had a few layers where you had hit points. So one here in front of the magnet and two behind, and with that you did tracking. And you had only a few tracks actually in this small acceptance. You had also Cherenkov counter, but now tuned for kaon identification. This is where it's built for. So this 100-ton magnet, you had to rotate around the interaction point to actually cover a larger phase space. With a small angle rotoscope, the experiment was able actually to do also flow measurements. So only very briefly, I will mention FOPI. So this was somehow in between chaos and Hades. So the big new thing here was that this energy's resistive blade chambers were installed for a much better time of flight measurement and very good identification of pions, kaons, and protons. So one of the I would say, latest detectors which are using or which were using drift chambers for tracking is the Phoenix experiment at the relativistic heavy ion collider. So the operation time was from 2000 to 2016. And this was, in principle, it's not, you don't perfectly see it here, but it's a two-arm spectrometer. So you had one here and one on the other side. You also had forward and backward detectors for muon identification, and in between a magnet. And then the drift chambers for the particle tracking. So that the new thing here and the update to the previous experiment was that you also have colorimetry. So something we actually had already in the plastic ball experiment, but here, of course, much higher granularity. So this could be used for direct photon measurements, jet reconstruction, and electron-positron identification. Another big step forward is the data taking rate, which is actually very good for those drift chambers because they are relatively thin. You can the drift time of the electrons which are produced in there is relatively short. That's why you can have a high data taking rate. And this was in this case about 5 to 6 kilohertz for gold-gold collisions. So some of the major findings, not only at Phoenix, but also, of course, at STAR, but to show here now the Phoenix results is the high momentum suppression as a function of for central collisions. So you see here, for example, for pi zeros, the RAA, the nuclear modification factor, as a function of PT. So for peripheral collisions, it's flat. And for central collisions, you have this large suppression, which is identified as an indication for the energy loss in the quark-gluon plasma. Also, the shape size suppression. So here you have you deal with charm particles was measured at Phoenix and also at STAR. You see it here as a function of number of participating nucleons, and in comparison actually to results from SPS, and this turned out to be very similar. So here you mainly deal with this dissociation physics of charms in the QGP. So now I switch to TPC-based experiments. As you will see, TPCs have quite big advantages, but also one disadvantage. They had it in the past, actually. It's not anymore the case, namely the readout speed in comparison to those drift chamber-based experiments. So I start with the EOS, experiment equation of state. Again, at the Beverluck, as you see, there were those three major experiments, the plastic ball, EOS, and DLS. So this is now a TPC. So you have, again, a gas field volume, but now you have a drift field with a large high voltage. And this, this means the particles are ionizing the gas, and then the electrons are drifting to the end plates. You can measure them. And by doing it right, you can actually get a 3D reconstruction of your particle tracks, as shown here in this lower left picture. And this is a huge advantage for a high dense environment. So if you have not only, as shown here, a few dozen tracks, but a few thousand or 10,000 tracks, you actually need to have a good tracking to really distinguish them. So some dipole field forward detectors. So first TPC for heavy ions. You see is a data rate 1 megabyte per second. This is very low for nowadays standards. For this time, of course, it was a lot. 15,000 pets. So remember this number, then we compared later on to what we have in new TPCs. And 10 to the 5 events in total. This is also something we can do nowadays in a couple of hours. So very similar to the previous experiment is actually NA49, so North Area 49 at SPS at CERN. So you see this kind of setup of this box-like TPC with a dipole magnetic field is in principle very identical to the EOS one. Here was a setup with two so-called vertex TPCs and then two main TPCs, and used for particle tracking, but also for particle identification. So it's something I'm going to show you in a few minutes, how this is actually done with TPCs. Time of flight was at the end for particle identification. So this is a quite unique setup with multiple TPCs, but here I think you clearly see how the evolution was going from EOS to this kind of larger experiment. So for the first time, we were actually had the energy density to create a QGP at the NA series experiments. So you see here a picture as for the EOS, how it looks like, the reconstruction of those particle tracks in those multiple TPCs. So this is very nice. And you see how important it is for such kind of dense environment. So here you couldn't simply place 3 drift chambers and say, okay, now how do those individual hits combine to the tracks? This wouldn't be possible. So one of the major, or I would say, most discussed results from NA49 is shown here on the right-hand side. It's a K to pi ratio as a function of square root S. So they actually did a beam energy scan. And you see this famous horn here. And this was discussed as a signature of a phase transition from the hadron gas phase you have here up to QGP. So more SPS results from NA60, NA50, NA57 are shown here. Just briefly want to comment on them. So here you see dimuon spectrum after background subtraction. You see the rho in comparison to model calculations. And here the in medium rho modification was discussed, chiral symmetry restoration, and so on. Shape size suppression I already showed you in comparison to Phoenix and star results was also done here at SPS, and you see how the shape size are suppressed with increasing centrality. Strangeness enhancement is shown here, so as a function also as the number of participating nucleons, so how it is going up, and also actually in comparison to star results, which looks qualitatively quite similar. And this was also discussed as a signature for quark-gluon plasma creation. So now I come to the star experiment. So this is a solenoidal tracker at RIC. So at the time it was built, it had the largest TPC for tracking. Again, this is not only used for tracking, but also for particle identification. I'm going to show you on the next slide. You see, this is now surrounding the interaction point. It's a collider-based experiment. So you have full azimuthal coverage, large coverage in pseudo-rapidity, and excellent tracking capabilities, actually. So it had also a time of flight system, and recently, recently means 2014, the first MAPS-based silicon pixel detector, something I discuss at the end of the presentation. This was not only, the star was not only operating at 200 GeV, so the maximum energy, but it actually did several beam energy scans from 7 GeV to 200 GeV, and recently also fixed target experiments. So the data rate at the beginning was just a few hertz, and recently it was going up to about 2 kilohertz for gold-cold collisions. So you see, this is not a static experiment. Such kind of things evolve over time. And before I show you this kind of evolution, I just want to show you how those TPCs are actually used also for particle identification. So you measure the relative energy loss of those particle tracks in this TPC. And if you plot this as a function of momentum, you can clearly distinguish those various particle species. So this is another huge advantage of a TPC compared to those drift chamber-based experiments. So, and again, the disadvantage of the low speed is actually nowadays in principle solved. And this is something I show you once we go to the GEM TPCs. Time of flight reconstruction for particle identification is also very important, as you see here. So clear distinction between protons, kaons, pions, and so on. And only with a TPC, you are able to reconstruct weak decay particles like the omega plus, for example. And for charm reconstruction, you need this kind of silicon-based inner tracking systems. And then you can reconstruct particles like a D0. So here you see this kind of evolution I just mentioned. In 2000, star started somewhere here with at 2000 with an event rate of a few hertz and a maximum energy. And then the event rate dramatically increased to about 2 kilohertz. On top, they did those beam energy scans. Here you see beam energy scan phase 1 and beam energy scan phase 2, which is still ongoing. In addition to collider modes, they also do fixed target and go down to very low energies to about 3.5, 3.8 GeV in square root S with a few 100 million events per beam time. So this is even large statistics. And this is going on right now at STAR. So some of the famous star results, and of course, most of those results were also done by Phoenix. This was elliptic flow. for identified particles, for centralities, various particles. You see here, you see shape size, here, pions, kaons, d mesons, and so on. Number of constituent quark scaling was discussed at the RIG experiments as a possible connection to quark-gluon plasma formation. Another big goal just in the past 10 to 12 years is the B-Mensch scan, and here the identification not only of the phase boundary between hadron gas and quark-gluon plasma phase, but also of the critical point, for example, by doing those net proton fluctuations. And this is also discussed, of course. Is there a question? Sorry, I hear someone. Okay, so a very similar experiment is the Dls experiment, so large ion collider experiment at LHC. So a central TPC. This is now the world's largest TPC, 5 by 5 meters. But you see the setup is very similar. So you have the central TPC surrounded by a few other detectors. For example, in yellow, the transition radiation detector for electron identification, time of flight, colorimetry, and also in the inner part, second generation maps-based detectors for D0, lambda C, and so on, reconstruction. So same issue in the past with relatively low data taking rates of about 1 kilohertz for LED, but in about a year, we will get up to about 25 kilohertz with an upgraded TPC, as I will show you. So here you see a picture of Dls, how it looks like in Geneva, 60 meters underground. You see here a person, you see how huge those experiments are nowadays compared to where we started in the beginning of the 80s. So here is also a picture how the TPC actually looks like. So you see here also people. This is 5 meters in diameter, 5 meter length. You see here the inner cut. And again, I'm not going into the details here. I just want to point out that this TPC had in the past 560 million readout pixels. So in comparison to the 15,000 I pointed out at the beginning at the EOS time projection chamber. So some of the Dls results I highlight here. So the RAA of shape size in comparison to what we had at RIG. So this was RIG that I showed you before. This is at Dls, and you see this is lower, the suppression is less. So here you deal with a recombination of charms, and this is changing the suppression. Also, what was measured is the nuclear modification factor of other charm particles like the D sub S, as you see here, to relatively high momenta. So this is the upgrade I was talking about. So, and this is, I have a lot of people talking.
Can you please all mute yourself? It's really disturbing the speaker.
So the TPC is upgraded from this old style gated way of taking data to gem readout. So the gems are thin foils with tiny holes with a large voltage difference between up and downside. And this is in principle giving us a gain. So here we get this avalanche effect, this electron multiplication. And with this kind of setup, we can do a continuous readout, and that's the next big step in those detectors. So we don't have this kind of trigger readout where we say one event, now next event, and so on, going to just a continuous readout. And the ion backflow, which is also important, is relatively small here, but it's still actually some kind of issue, but one can deal with this kind of problems. In a tracking system upgrade, this is also installed. You see here how many pixels we are dealing now with 12 times 10 to the 9 pixels. This is all maps-based, very small radiation lengths. This is reducing the multiple scattering import, for example, for electron-positron measurements. And now I will talk just a few seconds about software, because this is also a next big step in this evolution of our experiments, that we go away from this trigger-based event-by-event measurement to a continuous readout. So we have to deal now with 50 kilohertz interaction rate, continuous readout, 3.5 terabyte of data per second, what we get in here. And this has dramatic consequences for how the software is written. And this is what people are working on for a few years now. So the perspectives for 1.3 you see here. So again, Ds and Bs, RAA measurement now to large momenta with relatively small error bars. V2 measurements of such kind of particles, of charm particles, including lambda C to momenta, as you see here, up to 14, 15 GeV. So the MPD is a detector under construction at the moment. It's a multi-purpose detector at the nucleotron in Dubna. It also has TPC as a central tracking detector, resistive plate chambers for particle identification, time of flight system. The big advantage here of this detector system compared to what we had before is that this is actually collider. So this is what I pointed out at the beginning. The acceptance is not really changing with energy, and it's actually doing an energy scan from 4 to 11 GeV with large interaction rates. So significantly larger compared to what STAR can do at the moment with a beam energy scan. And this is where the collider was actually optimized for. 5 minutes, okay. The S-Phoenix experiment is also under construction. This is at RIC. It has nothing in common actually with the Phoenix experiment, except mostly the collaboration. It also has a GEM-TPC as a central detector and surrounded by various other detectors similar to what I showed before. As you see, this kind of setup, STAR, ALICE, S-Phoenix, those are all very similar in the way they are built. What is changing here is that it has now also this kind of continuous readout, as I pointed out for ALICE. And with that, we can go up to about 15 kilohertz readout rate. And the focus here is on hard probes, ypsilons, jets, heavy flavor, and so on. So here you see some predictions from S-Phoenix for ypsilons and also RAA for jets, hadrons, and so on, going to very high PT. So at the very end of the past few minutes, I will talk about the latest stage of evolution in heavy ion experiments, experiments which are mainly based on silicon technology. So monolithic active pixel sensors, this is what MAPS stands for. I mentioned this term a few times before. So here we have radiation hard pixels, very compact integrated electronics, very thin, and this is a big advantage of this detector technology. First time used in STAR, now also in the second generation here in ALICE, as shown in this picture here. So you see how dense it is, so many layers of those pixels, tiny size of the pixels with very good resolution. This is actually needed for D0 reconstruction, for example. So the next step, and this is under development at the moment, is so-called bent alpide. So you bend those chips around a tube, and with that you can get, of course, a much more compact detector design and with a good coverage in your acceptance. So the CBM experiment at SIS 100 is also under construction. It stands for Compressed Baronic Matter Experiment. It's also, as a main tracking detector, it's using silicon technology here in several layers, surrounded by a magnet, and then several layers of various detectors I already mentioned for previous experiments. So Cherenkov detector for electron positron identification, transition radiation detector we had also in ALICE, time of flight, electromagnetic calorimeters. So this important part here is that the readout rate is gigantic of about 10 megahertz. So this is really the maximum we will have in the next few years. You see here's a timeline. So it will start in 2025 to 2027. And the physics agenda is about a phase transition, a critical point, chiral symmetry restoration at large baryon chemical potential. So that's why it can reconstruct actually dileptons and also dimuons, strange matter, so double multi-lambda hypernuclei. And they even discuss heavy flavor production at those energies. So at the very end, I discuss the ALICE 3 experiment. This is under development, not even under construction. So this is what people are discussing at the moment. So this will replace then at some point in the ALICE experiment at the LHC. You see the dimension here, it is 2 meters in diameter and 4 meters in length. It's much smaller compared to the existing experiments. In principle, all you see here, all the yellow, green, and so on, this is silicon at the end. So you have many silicon layers, so you don't have this gas field detectors anymore. This means you have super fast readout, and this goes to 50 to 100 kilohertz. So you can get a lot of many events per second. You have perfect resolution. This means you can identify D mesons, lambda Cs, and so on. And you can go to very low momenta in PT, because those MAP-based detectors, they are very thin, and the multiple scattering is low, and that's why you can go to this very low PT. So the physics idea here is that you to go to really very rare probes, for example, lambda CCC, low PT observables, and also dielectrons to look into chiral symmetry restoration and so on. So this was my presentation. So I thank you for your attention, and I also want to thank all the people here for providing materials and helping in setting up the presentation. Thank you.
Okay, thank you very much, Alex, for this leading us through 30 or 30 plus years now of high energy heavy ion experiments, from the Beverlac to the LHC and then back to HES energies at the FAIR facility. Let's see what we have in terms of questions. Let's see whether there's anything in the chat. There's a question by Mike Lisa about the magnetic field in ALICE 3. Do you want to say something, or should I?
It's better if you answer this. I think you are more an expert in ALICE 3.
It's not really fixed yet. A possibility would be to stay with the L3 magnet, although the aperture is really much larger than what we think we need. And also it's an old magnet and a warm magnet, and power converters are very difficult to replace. But it seems that half a Tesla is enough for the physics we want to do. For some physics, even lower fields would be better. If you think of the low mass dielectrons and of effective Dls rejection strategies, they benefit. We actually in ALICE, we will turn down the magnetic field to 0.3 or maybe even 0.2 Tesla for a special one. So the field, the magnet, the central magnet will be a solenoid, and it could be the old L3 magnet, and the field will definitely be a low field. I don't see raised hands. I could maybe add to this a tiny comment, and that is one of the goals we are thinking to address again in ALICE 3 is testing the low theorem, this controlled divergence that you have in all field theories when you go to very low energies. And that would be a dedicated, very forward spectrometer where you measure the very low energy photons down to 30 or maybe even 20 MeV, and that would need a small dedicated dipole magnet.
Yeah. I mean, this is, I talked to Klaus about this. Of course, there are some problems with Bremsstrahlung and so on, but this is under investigation at the moment. I mean, as I pointed out, I mean, ALICE 3 is in the planning stage at the moment.
Yeah, so people could expect a letter of intent by the end of the year, of this year. I still don't see any questions, but you can always send email to Alex if you have some specific questions. Let me see whether there is something more in the chat. Ah, yeah, okay, so there's a question by Udita Shukla to everyone. Could you elaborate on the implication of RAA suppression at high momenta? you could take a start, Alex, but then it's maybe a question to everybody.
Yeah, I think this is more a physics question to everyone.
So, I mean, it has been measured now at the LHC up to a few hundred TeV momenta, so a good fraction of the beam energy, and RAA seems to stay at about 0.5 or 0.6, and I do think that starts to be a challenge for models.
So is the question specifically, for example, about S-Phoenix? I mean, because here in
does not specify. It only says
yeah,
high momentum.
Yeah, it is about S-Phoenix. Yeah.
But
so
S-Phoenix,
I mean,
high momentum, it's our low momentum.
Yeah, to be honest, I mean, we discussed this, or I discussed this also with other people, and it's not 100% evident what we can expect, which kind of difference we can expect to the LHC, where we get to higher momenta already. This is a very good question, but this should be actually answered by S-Phoenix.
I don't think we have anybody here from S-Phoenix, at least when I scrolled through the participants. Let me see. Yeah, so thank you is what Udita Shukla says. And yes, it was about S-Phoenix.
Yep.
For
the charm light particles at least, of course, I mean, here we don't have the coverage at the moment. I mean, here it definitely makes sense to go to larger momenta. But yeah, very good question about a comparison S-Phoenix to LHC energies.
So I don't check the chat once more. I don't see any other questions. That means we still have some coffee break left. So let's first thank Alex Schmah again very much. And then I understand from the organizers that they would like to start as was planned. So at 4 o'clock Central European time, or whatever your time is. However, I think Masoud wants to ask everybody to disconnect, that he can rearrange some settings and reconnect, but I let him speak himself.
Thank you, everybody. I'm just going to adjust some settings, but we will start exactly as scheduled.
So will you throw out everybody by ending the meeting and restarting it, or what do you propose?
Just end the meetings and
get some coffee and come back in time.
Yes.
And there are many people present to let you back in.
Yeah. Thank you very much, everybody.
Okay, so then let's close this session and come back in time for the next session.
Thank you.